I'm Aaron Blahowiak. I have 10 years bringing down production, learning how and why that it happened, and trying to figure out how to stop it from happening again. I'm still working on that part. On social media, I'm at Aaron Blahowiak on Twitter and Instagram. I picked that even though it's tricky to spell because I thought it would be a unique identifier, but I'm not the only Aaron Blahowiak on Twitter. So, accept no imitations. I'm the one without a tie, and I don't tweet about hockey. On Instagram is mostly woodworking stuff, so if that's relevant to you. I hope that this is a good talk because we literally wrote the book on chaos engineering. I'm the first author on the second line. And I did write the chapter on blast radius minimization and contributed minimized blast radius to the principlesofchaos.org, although I did not come up with the idea. I am also a new father, and thank you. We had a baby in January, and he's still learning the art of sleep. So if what I have to say sounds like my head's in the cloud, it's probably why. If any of you fall asleep during my talk, I'll assume you also have a baby at home. So today we're going to talk about the need for precision, our early forays into precision chaos, the current state of the art, future work, and an experience report. And I probably won't be reading the entire slide for the rest of this. So what is the most, I'm a liar already. What is the most famous chaos experiment? Does anyone have any ideas who doesn't work with me? All right. Well, it was April 26th, 1986, which I realize is before some of you were born. And it was the Chernobyl accident. So, a little disclaimer, I'm not a nuclear engineer and I'm not a historian. This is my reductivist understanding of the events that happened then. So, a nuclear power plant is cooled by water. The water gets into the reactor with pumps. No pumps, no cool water, bad times. The pumps usually use the electric grid for their power. If the grid's offline, they had a fallback, which is diesel generators. Those generators take between 45 to 60 seconds to spin up to be able to produce enough electricity to power the pumps to get enough water. The nuclear engineers thought that this was not optimal, and they could come up with a fallback to their fallback. That fallback to the fallback was to use the residual waste heat in the reactor chamber and the residual momentum of the turbine that the steam powers to take that electricity and then pump that to the pumps to keep the water flowing. So they were experimenting on this design that was the fallback to the fallback. They had actually experimented on this several times before for a few years leading up to the accident. None of those prior experiments had actually produced sufficient electricity from the turbine to power the pumps. They really wanted this to work. In order to run their experiment, they had to disable automatic safeties. So when they ran this experiment the last time, due to a variety of factors, including that desire to really make it work, influenced human decisions at the time that led to an excessive buildup of steam, which led to a steam explosion, and then a secondary explosion that launched radioactive material into the atmosphere. It's one of the two worst nuclear accidents in human history. It and Fukushima are the only INES Level 7 nuclear accidents. The government of what is now the Ukraine, has said that the land there will be unfit for human consumption for 20,000 years. The point of this talk is to be precise in your experimentation, to use the least scope possible to impact the fewest users in the safest way possible. So, Tammy said this, or something close to this, at her session on Tuesday, that chaos engineering is the facilitation of experiments to uncover systemic weaknesses. I really love this description. As an empirical discipline, we find truth through experimentation. We put hypotheses to the test. When you write some code, you hope it works. You might even believe that it works. When you write unit tests, you still build some confidence that your analysis and the things that could go wrong is correct. However, Experimentation is the difference between suspecting and knowing, gathering evidence in production about the way that things actually work. The job of the chaos engineer is to create systems to allow others to experiment. So we create the infrastructure, we streamline the best practices, and we educate users, evangelizing availability. The tricky part is, how do you uncover systemic weaknesses without causing cascading failure? So which experiments should we perform? There are many different things that we can look at. The way I like to factor the problem is to look at the frequency of the events and weigh them against the impact that they would have on your users, and also the costs of performing those experimentations. The more impactful an event would be, the more that I would want to run that experiment. For instance, Chaos Kong is an ongoing experiment to resilience of regional failure. It's very complex and costly to do. Well, not very costly, but it is costly to do. But it has a huge impact and really saves a lot of customers from experiencing pain. Every time Chaos Monkey picks an instance to send softly into that good night, it's a little experiment on the hypothesis that we're resilient to instance failure. It happens all the time, and it's very cheap to do. Both Monkey and Kong are examples of hardware or infrastructure failure. But here's a very sad graph. It's the outages by the days of the week. We have met the enemy, and he is us. So Walt Kelly was a cartoonist. This quote is from 1971. Unfortunately, he died in 1973. The quote was talking about litter and climate change, but it sadly also applies to software engineering. So one way that we measure availability is the stream starts per second, how many people are actually successfully playing back at Netflix. And our core team, a group of SREs that's a centralized team, has analyzed our incidents. And they found that 40% of our missed streams were due to a software bug. That's by far the largest category. This is the smallest ratio that I've seen at any company that I've worked at, but it's still too high. You might make the argument that every missed stream is a result of a software bug, but I disagree. We don't actually plan or expect to be resilient to every single eventuality in production. The takeaway is that we shouldn't be focusing on instance failures. We should be focusing on pernicious code. So we love Chaos Monkey. My stunning colleague Lauren recently finished a big revamp, and it works great. It's fantastic. It integrates tightly with Spinnaker. If you're using Spinnaker, drop in Chaos Monkey and you're ready to go. The thing about Chaos Monkey is it worked. In many ways, it's also kind of done. It runs on autopilot, so we can focus on bigger fish. Since it's been out, we actually haven't had a major incident caused by an instance failure. Moving on, one of the things that we decided to do was to look at latency. Latency is one of the worst things that can happen in production because it keeps you hanging on, you still have hope, and you're waiting for an answer. We've all felt that way sometimes. When things fail fast, at least you can start working on the next thing. Before my time at Netflix, they wanted to understand the impact that latency of downstream services would have on an upstream. So carefully, experts looked at thread pools and circuit breakers, disk usage, all of the different levers that we had for resiliency, and they determined that everything should be fine. So we picked a very seemingly unimportant, non-critical service to begin experimentation upon, and started with just a little bit of latency. Everything seemed fine. So we took a bigger risk and added a little bit more latency. Everything still seemed fine. Then we hit a tipping point where some of the circuit breakers started to open, so those requests wouldn't happen anymore. Still, things are fine. Eventually, we saturated thread pools. Still, things were fine, things were kicking in just as they should. And as the system was going, it was returning errors, because it wasn't critical, and that's what it was designed to do. Little did we know at the time that at our actual gateway layer, there's a generic circuit breaker that sees if the error level itself is too high, well then maybe we're experiencing some sort of systemic issue and should start shedding load. And when it does that, it does so indiscriminately. You nod like this is a familiar song. So the impact of this experiment was larger than anticipated because we crossed the critical threshold. Unfortunately, the experiment was manual, and we didn't have automatic short-circuiting built in. So we caused undue customer pain, and this really rightfully made engineers scared of using latency monkey in their systems. Now, we didn't spoil the land for 20,000 years, but we did find the need to find a better way. Latency monkey, like many of the monkeys, has since retired. When we have a change to make, we should always seek to find the smallest scope that gives us confidence the change is a good one. Then widen it until the change is done. Understand your rollback strategy beforehand. I love this quote. So Matt Jacobs wasn't talking about chaos engineering when he said it. He was talking about change management in general, whether it should be configuration management, whether it's a new version of a code, a new scheme for sizing instances, whatever it would be. To summarize it, take small risks, and then progressively take larger risks as you get more confident that they'll be a success. Have a way out. Finally, we're starting the talk. So precision chaos is using the right tool for the job. In woodworking, we progress through a series of tools, from the coarse, sometimes a chainsaw, to fine, like double-aught steel wool. So we can start removing the most material quickly and then move our way down the coarse to fine chain to get to the most precious little bit of material removal. In chaos engineering, we want to do the exact opposite. We want to start very, very small scope, small changes, and work to increase our scope as we get more and more successes until we're doing the maximum perturbation of just shutting down production clusters. So precision chaos is a collection of tools and techniques used to minimize that blast radius for our experiments. FIT was an early attempt at precision chaos. We wanted to induce unusual events for some people, not for everyone. I don't think Colton, the person who came up with FIT, thought of it in those terms, but the spirit of that idea was there. So instead of just making all calls to the personalization service fail, we could make some of them. So at Netflix, we serve a personalized experience, continue watching bookmarks, et cetera, et cetera. If that system's down, we should serve you a fallback experience that's generic, but at least you can still watch stuff. So in this experiment, we'd have, for instance, 1% of users that we would impact. When their request comes into our gateway, Zool is open source, they get tagged with a header, and that header propagates throughout the rest of our stack using an AWS or ribbon in the request context. Inside API, when we make a call to that personalization service, we check that header. If that header says this request should have failure injected, we do that. An exception gets thrown, triggers the fallback path, that gets returned to the user. Of course, API isn't just one server. We have many instances in production. So this failure is spread out among all of them. We call this a diffuse experiment. This diffuse nature means that you won't cross critical thresholds. We run our systems with headroom to accommodate for the natural variance and baseline error load and the daily cycle of viewing habits. With small-scale diffuse experiments, you can easily stay within that headroom. This means you never hit critical thresholds for things like utilization, saturation, circuit breakers, etc. Basically, this is fallback correctness testing. So here's the result of running a FIT experiment. With FIT, we analyze the impact by looking at the aggregate statistics. Even at our huge scale, our signals have a high variance. The high variance makes it hard to run a very small experiment that was useful. Colloquially, if you run a 0.5% experiment, but your variation is 3%, there's no effect size that is going to show up and be above noise. More rigorously, it's a power and sample size issue. To achieve a very high level of confidence in the face of high variance, you need a large sample size. To make up for this, people were running experiments where they would ratchet up the percent of people that were impacted. Sometimes things would be fine. Sometimes there is a linear relationship between the number of people that were exposed to the failure scenario and the amount of pain that we could detect. And then we could end those experiments. Unfortunately, sometimes there are discontinuities in that curve. And when that would happen, things would be progressing fine, progressing fine, progressing fine, and then they would be very not fine. We'd end up with way too many people with a degraded experience. Another approach would be, instead of ratcheting up the percentage of people impacted, you could run a longer experiment over time, and then you'd still be able to detect slight variations between your baseline signal. That just spreads out a lot of pain over a long amount of time. These experiments were manually initiated with no automatic short circuiting. From this graph, can you really tell if there was an impact? I always feel like Titus when I run chaos experiments. So maybe you thought there was a dip, maybe you didn't. Using statistical techniques, we analyzed the data and we couldn't confidently determine one way or another. It's in the noise. Let's dive deep into that. So we're running an experiment that has 0.5% of the people that are going to be in it. Oh, disclaimer, I'm not a data scientist, statistician, or a mathematician, so this is a simplification that will hopefully give you an intuitive sense of the problem, even though these numbers are probably wrong, so please don't correct me on Twitter. So we have this experiment with 0.5% of people. So the real impact of this experiment would be a loss of, say, 2 events per second in a baseline of 1,000 events. Made up numbers. So in aggregate, the normal range in our variance would be from 970 events per second to 1,000 events per second. And in the experiment, that shifts that range down to about 968 to 998. With the segmented signals down below, if we look at just the experiment population versus a same-sized control population, we see that the the control population goes between 9.7 to 10, and the experiment goes from 7.7 to 9. So even though it's the same data shown in both graphs, you can definitely see and even statistically tell that there is a variance between these two lines. So we can now do this with our diffuse experiments, although we couldn't prior. The person who created FIT initially and did chaos engineering at Amazon before Netflix has left Netflix and started a company, enterprise chaos company, I guess, called Gremlin. I can't vouch for it, but it might be cool to check out. So CHAP. CHAP was designed to overcome the limitations of FIT, focused on minimizing the blast radius, providing clear signals, and high confidence. CHAP takes FIT and it adds more orchestration, automation, and safety. It isolates the statistics of the experimental group and it concentrates the failures onto dedicated instances. CHAP works kind of like a sticky canary. We deploy new clusters, for instance, the API control cluster and the API experiment cluster, and then we route traffic to those clusters. So it's not taking the main rest of the pool, they're totally separate, but this is live production traffic. In this case, 0.5% to our experiment, 0.5% to our control, and 99, the remainder, going through the main cluster. Now here, because all of the experiment group is on one box, 100% of the calls from that set of API service to the personalization service are going to fail. This makes it so that you will saturate your thread pools, you will hit your critical thresholds for circuit breakers, hopefully, if they're tuned. And it'll give you a nice signal of those machine statistics, such as CPU usage, etc. And we leverage our existing automated canary analysis tools and techniques to analyze the results of these chaos experiments. So we call this a concentrated experiment because all of the badness is in one box. We contrast that to the diffuse experiment of the FIT. So here's the result of running a CHAP experiment. This is the real result. As you might expect, serving the fallback experience without your continue watching, etc., does reduce the amount that people watch movies, but it doesn't go to 0. So hooray. The experiment lasted only 9 minutes long. We set them up to run longer than that, but we detected this divergence and we exceeded our error budget for the experiment, so it was automatically aborted or short-circuited. In this way, we can run very small experiments that have very high confidence in the results, so it's very safe to do and yields very high-quality information. A little bit more about CHAP. So many users, when something doesn't work on one device, they swap to another device. So we shard by device and user, which gives us a really high-quality signal while minimizing the pain to our customers. So when they do that substitution behavior, they will usually get out of the experiment group. We use a streaming platform in order to gather and analyze population statistics and behavior statistics for the experiment and control groups, so we can check for divergence and also make sure that the cardinality of both is the same. We also leverage, like I said, the automatic canary analysis things. We do the short circuiting, and we have Spinnaker integration. So people have put CHAP into their deployment pipelines. Now, I hate it when some expert ninja rockstar guru scion stands up and preaches their one true path to righteousness as if they can do no wrong. So here's what we don't like about CHAP. If your production cluster has a small number of instances, let's say it's 3, and you run an experiment. Well, we spin up our experiment and control cluster, each with an instance, and we start routing traffic to it. Well, now your experiment and control cluster have 1/3 of the traffic each, so you've taken away 2/3 of the traffic to prod. What are your auto-scaling rules going to do? They're going to downsize that production cluster. When the experiment ends, all the traffic goes back to the main production cluster, and sad times can result. Another thing is that our traffic varies greatly between morning and night in each region because people don't watch Netflix while they're at work much. So we auto-scale throughout the day. So we have to limit the time of our experiments so that the tide of traffic doesn't cause our experiment and control clusters to be out of proportionality. Our failure injection and routing is in process, which is great in terms of flexibility and the ability to really know what's going on. We want to have stack traces and debugging and such. But it means that we have to redo this for every language that gets added to the beautiful garden of Netflix server stack. If instead we had gone with a service mesh approach in our platform at Netflix, we could have done things out of process, and then we'd only have to do it once. Also, CHAP isn't open source because it's so tied into the things that Netflix does. However, Envoy or Istio does have the ability to have latency and failure based on their complex rule system. So one could imagine such a system being built into something like Kubernetes. There's an open ticket for Linkerd, so if you're one of their users, like upvote it or whatever GitHub does. So when we think about experiments, we can categorize them into a beautiful 4-quadrant graph. My dad did this sort of thing for a living, so I apologize for subjecting you to 4-quadrant graphs. So sticky is what we've been talking about, where you hash based on the user and device. And that gives you a really good signal because it lets you know how the device behaves as well as being part of the failure. The random is great because it doesn't subject the user to the problems because the next request that comes in will likely be out of the experiment group, and so you'll mask the pain that you would be inducing otherwise with the retries. So with a random concentrated experiment where you have non-sticky requests coming in but all getting routed to that experimental cluster, you can see the load that the fallbacks or latency would induce on your experimental cluster, which is great. And you can see the resource exhaustion and also the result of server retries. So sometimes when there's an issue, your upstream decides, oh, maybe if I try 20 more times, it'll be better. And that's good to be able to detect that without subjecting customers to pain. With the diffuse sticky things, you can test fallbacks, basically like fit, like we talked about. And the sticky concentrated does all of the above, plus it checks device retries, which can be substantial, especially with 100 million users. As a quick note, so did people here watch Peter's talk yesterday morning? Yay. Okay, some. So LDFI searches the state space of failures in your dependency graph using basically a graph exploration algorithm. Peter, feel free to correct me on Twitter. But that basically automatically creates sticky diffuse experiments, which is awesome. It can expose ways that your system is prone to failure, but it won't show what happens in terms of the load impact when you get concentrated failures on a machine. And that's important because it's a different, new, additional set of failures that you need to be able to determine in production. For future work, we want to be able to track the users that are actually impacted by the failure injection, not just the users that fall into that bucket. For instance, you can imagine that we would have different DRM services for different types of clients. If we shut down the DRM service in an experiment for one device type, we would still see successful play starts in that experimental population because people of other device types would be hashed into that bucket. And so what we'd really like to do is be able to track those users who actually had a failure injected into them. And then for the control population, track those users who would have had a failure injected into them. That would be a little bit more precise and reduce some of the noise in some of the experiments we have. In the spirit of wanting to minimize customer pain, I would love to be able to run a few different smoke tests on a device or web browser, Selenium you can imagine, against a failure scenario before we even subject customers to it. I call this smoke test as a service, and I think it would be super useful for things like canaries or even mid-tier service developers who just want to know, did I break a device without having to go through a canary process? And finally, right now when we have failure, it's 100% failure or no failure. Or it's the same amount of latency added to every request or no latency at all. I would love to be able to describe a probability distribution of failures, because that really matches production. Rarely does your system go from 0 to 100 like that. Similarly with latency. This starts to get at the notion of gray failure, which one of my stunning colleagues, I think this is Lauren again, had pointed out. And just Google gray failure, you'll find the blog post that links to the PDF that you can download. And finally, I would love to be able to automatically increase the scope of our experiments. Right now, we can do it by setting up Spinnaker pipelines where you have each different kind of experiment in a pipeline, but you should be able to just specify your failure scenario, and we should generate that automatic chaos progression. Speaking of which, so we start with very safe experiments that have low external validity. So that external validity thing means that it doesn't really match what happens in production, but it's still useful because it helps build confidence. And then we just progress. And at the end, we're doing high risk, but very high external validity experiments with very high confidence. So each step along the way de-risks the experiment. And it builds confidence. So by the time that you're getting to that final large-scale experiment, it should be low risk on a risk-adjusted basis, but still high risk in terms of maximal negative impact. So that's why you want to work up to it slowly. One thing I'd like to point out, with random concentrated tests, you can do hill climbing to find inflection points for latency injection without negatively impacting customers. You could also do things like squeeze testing. It's like shadow traffic, but better because it's real traffic and it hits your real databases. So do I still have time? Yes, I do. OK, so what happened last week? So we had a tiny chap experiment that ran. It found something very interesting. And right around when the experiment short-circuited, there was a noticeable dip in SPS in the region in which the experiment had run. The recorded miss lasted under a minute. So this is 1 minute drop, but that's the finest granularity that we have. And it was curiouser and curiouser. And it's usual that after we see a drop, we see an uptick because users are trained to retry. And so we had an an incident that was filed. And that was, kind of nerve-wracking. So here's the experiment that ran. It only ran for about 4 minutes in actuality when we detected that we exceeded our error budget and automatically short-circuited. And we started investigating. How could our experiment break out of its cage? It was a very lovingly, specially crafted cage. And we looked into it. Usually when things fail, you see error rates go up. Well, we didn't see that. That was weird. Then sometimes you'll just see, well, retries might have masked the problem. There was actually not an increase in traffic, but a decrease in traffic. And that's very odd. Turned out that that was the smoking gun, if you will, for what we now believe the problem to be. One of my other stunning colleagues, Brian Tolson, suggested breaking out our requests coming in to our Elastic load balancers by country. So Brazil had a way larger drop than we saw in aggregate, and Canada had no drop. Neither did the United States. So, we don't shard by country when we run experiments, so we don't think it was us. So we'll never know if it was an internet interconnection fluke, the USS Jimmy Carter, or just some storm in the clouds. But for now, we really don't think it was a chaos experiment. To be sure, after calming down and reassuring ourselves that we were right, we reran the experiment later in the day, and we didn't see the impacts to aggregate SPS. So in conclusion, we talked about the need for precision, our story along the way, the ideas that we have for future work in the field, and I shared with you an experience report. Any questions? Thank you.
So we have almost 10 minutes for questions.
What's squeeze?
So squeeze testing is where you find when your server will melt under load by slowly increasing the amount of load you send it. So you had a question as well?
So how often do you run these tests?
How often do we run these tests? So our team doesn't run these tests. Other teams design and execute these experiments, and once they have removed all of the known vulnerabilities that they have, they incorporate them into pipelines which can run daily, multiple times a day, on deploy, et cetera, according to their team's freedom and responsibility and ideas of how resilient they need to be. Yeah, sure.
So does it ever happen that they're running it at the same time? Can it cause like a wider impact? Because if it takes more that
So the question is, can running multiple experiments cause a wider impact? We have mutual exclusion on the experiment groups that an individual can be in. So it is additive in the number of potential impact that you could have. And you could have another experience where we would cross the threshold for our generic load shedding circuit breakers. Because our experiments are now so very small, you'd have to run a lot of experiments in parallel. And we could implement mutual exclusion or like a semaphore counting. But right now, random is good enough for keeping us safe. Yes?
So you have your progressive
Yeah.
types of testing,
Yeah.
covering larger and larger scales. What magnitude of error budget do you have for those?
So the question was basically, we have this progression of chaos, and what is the error budget that we have, I guess, at the different layers when we're running the experiments. So that depends based on the criticality of the service under test. Some services believe that they cause no impact to our streaming, and for them we would want a very tight error budget, because if we detected one, that means things would likely go very, very wrong. Other services, like the personalization service, knows that they have an impact, but they suspect that that impact is not 100%. And so depending on the system under test, we would change the error budget. And when we design our error budgets, currently we have like a set maximum threshold and also a like percentage difference for variance as well. So like if you trip the percentage but not the maximum, we abort. Or if you hit the maximum but not the percentage difference, we similarly abort. Yes?
You mentioned that latency monkey was kind of canceled as a project. Was that because the people were afraid to adopt it after the first mistake, or was that because of some technical problem?
So the question was essentially, why was latency monkey retired? So, and the options provided by the brilliant audience member was it due to a technical problem or was it due to people not wanting to use it? And I think that people didn't want to use it because of the technical problem of its unconstrained blast radius. So with the chaos maturity model, which is a brilliantly written chapter in the free book, Chaos Engineering, we talk about the two axes of chaos maturity. One is sophistication, which describes not only blast radius minimization, but also the way in which you design experiments, et cetera, and then adoption as the other primary axis. So sophistication without adoption is satisfying for us, but not useful to Netflix or your company. So we really focus on the adoption of sophisticated tools. And you have to like, push the sophistication to drive adoption, and there's a relationship between the two. And you're welcome. Yes? Can I give some examples of simulating partial failures? So that would be things like where this personalization service, for example, wouldn't be returning 100% error rates, but rather would be returning error rates with a normal distribution. So you'd imagine that it would have sometimes error rates and sometimes not errors being returned. So it wouldn't be like 100% failed. So that would be one example. Other examples are where you'd have intermittent latency issues and things like that, which helps you to verify that like some load balancing technologies work and other things like that, where sometimes you have a weird instance within a cluster that can cause issues. And if you check out that paper, Gray failures, yes. Yeah, grave failure. They go in more into that and the other problems that you'd see from it. Are there any other questions? All right, well, thank you very much. I really appreciate it.